Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience.
Hi everyone. Today we have with us Steve Maguire, who is a staff scientist at Snow Lab in Canada, and who did his nano-related research work at the University of Ottawa. Hi, Steve.
Hello.
How are you doing today?
I am not bad.
Okay, wonderful. Could you tell us how did you end up in the nano or material science research field? How did that happen for you?
Well, I started my master's in December of 2003, and I showed up expecting to do a project on zeolites because the prof I had made contact with was working on zeolites, and I was really excited about zeolites. So I turned up and I said, "Where are the zeolites?" He said, "We're done with those. Here's a nano project." So he is a photochemist. So he does all sorts of chemistry by shining light on things. Mm-hmm. And he'd read a paper where someone else had tried to make silver nanoparticles by dissolving them in a polymer, like dissolving a silver precursor in a polymer film and shining a light on that. And that took half an hour, and it made this disgusting brown schmutz.
Okay.
So silver nanoparticles are supposed to be pretty and colorful, not supposed to be brown. So Tito saw in this paper that they were using photochemicals very similar to something he'd done in the 80s. So he figured he could adapt his system to make these things a lot faster. So then I turned up ready and eager. So he hands me this project. And what it was is, instead of using polymers, you do it in micelles. So micelles are, if you know what soap is, soap molecules have a long carbon chain and then a little polar end at one end. And if you put them in water, all of those nonpolar carbon chains stick together for protection because the nonpolar end does not like the water. The polar end does like the water. So you get this little blob. And yet what you have is a little hydrophobic environment in the water. So stuff that normally does not dissolve in water will go in there. And actually, that's how that gets the grease and the dirt off your clothes. So all of the chemicals we're using did not like water, so we hid them in these micelles. And what happens is when we shine a light on it, we make radicals, which is so normally you have chemicals in the molecules have covalent bonding. So when you have a bond between two atoms, each atom kicks in an electron. Those two electrons make a bond. If you hit it with intense enough or energetic enough light, like in the ultraviolet, you can split that bond, and then each of these atoms just has this half bond hanging loose, which is a single electron. That's a radical. And if you have the correct sort of radical, it can float around. It can find, say, a silver salt. So silver +1, so silver missing an electron, really wants that electron back. So it'll take it anywhere it can grab it. So it will grab this loose electron on this radical, make silver metal, and then it can find a whole bunch of other silver atoms and start building itself into a nanoparticle.
Okay.
So I did that, and then instead of the half hour in the paper, it took about 30 seconds. I turned the light on, I waited 30 seconds, I turned the light off, and I had this nice golden yellow solution. Except it took me about a year and a half to get to that point.
Okay, wonderful. All right. How and where does your nano or material science research fall in the domain, the bigger picture of the field?
I would say it is nano because it's simply making it's the synthesis of stuff we haven't seen before. It's not. Yeah. So my particular research focused strictly on just making it. I didn't look into applications or what we can do with it, or So it's the nano half of nanomaterials.
Okay. All right. Cool. And which research project are you most proud of? And could you explain it in simple words in the section, in other words?
So my proudest research project is the one where I was able to make silver nanoparticles in 30 seconds at room temperature with no exciting chemical, no harsh chemicals, quickly and simply.
Okay, cool. And I guess you also teach?
I do teach.
What do you teach? Which courses would you like to mention?
Mostly I've taught a lot of first year courses, so the introductory chemistry. And I'm most proud of that because a lot of profs treat first year as something they have to do. So maybe they don't give it as much excitement as they could. But in my first year courses, everybody passes. Well, the only people that fail are the ones that really worked at failing. Everybody who deserves to pass passes, and my class averages tend to be 10% higher than everybody else.
Wow.
And like I've had people tell me, like they've taken the course a second time because they've done badly the first time, and they've said they wished I had taught them the first time around.
Wow, that's really cool. If you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything. Just 3.
I would wish that I knew then what I know now. Not necessarily about what the answer is, but about how everybody struggles and how research is supposed to be hard because it's research. If we already knew what the answer was, it wouldn't be research.
Right.
Wish 2, I wish I had put a little more effort into knowing the background, because sometimes I still feel like a fraud when I don't know something that should be fairly obvious for photochemistry. 3rd wish, I wish it would just work sometimes.
You wish it works earlier, not like 1 year into your research. It works like 1 month into your research.
Yes, I just wish, I wish research didn't have to be as hard as it is. Like once in a while, something should just go right. I shouldn't have to beat my head against a brick wall for 6 months on everything.
Right, that makes sense. That's fair. I understand. I relate to the vision completely. As a former researcher, I relate completely.
I'm pretty sure everybody does who's ever been in the lab.
Right, they do. All right. In that case, what are you most looking forward to in the next 3 months?
Finding a job. My time at the neutrino lab is coming to an end. It's time to move on to the next step. I just am not entirely sure what that next step is.
Okay. All right. Then we wish you good luck with finding a job.
Thank you. I'm going to need it.
Wonderful. And before we end, could you explain or could you explore the challenges or questions that the field of nano and material science is facing today?
So the biggest challenge facing everybody today is obviously climate change. And chemistry and material science have an enormous role to play in mitigating this. So after I finished my nano research, I went on to try to do a PhD in biofuels. So material science and nano can contribute photocatalysts, just a way of shining light on water and getting hydrogen out of it. Because as it stands, we can put a lot of electricity into water, but that consumes a lot of electricity. As opposed, if we can have just some sort of nanomaterial on a plate, and you just stick the plate in the water and stick it out in the sunlight and collect hydrogen coming off like that, that is a huge contribution.
Okay. Interesting. So climate change, materials and chemistry field can help in the climate change, or trying to find alternatives.
Alternatives to fossil fuels, either hydrogen or even just catalyzing biomass into biofuels instead of digging it out of the ground.
Oh, okay. Interesting. Well, on that optimistic note, let's end the podcast. Thank you, Steve, for taking the time.
Anytime.
And we look forward to your curation week on Twitter.
I'm looking forward to it too.
Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.